Hi, my name is Dan, and this video is one in quite a large series of videos in which I'm charting the progress of creating a relatively simple 4-bit simulated CPU from the basic logic gates and building everything up and talking about the, the process and how things are being designed. Uh, There's a roadmap of where we're going in the description down below. We're quite late on in the process now. We're coming to the end of designing the control unit, which is an integral part of the CPU. And the software that I'm using is DigitalWorks. It's free to use software, and there's a link to where you can get hold of it also in the description down below. And I do hope that you're playing along with me. If you're just jumping in here, you've found this video for some reason on some kind of search, then it might not make a lot of sense because it builds on a whole lot of stuff that's previously gone before. But if you want to go through this experience of building a 4-bit CPU and understanding what's going on inside a CPU, there's lots of differences between different CPUs, but it should give you a good understanding of some of the issues in CPUs. Then I would invite you to get the software and start at the beginning of the videos and play along with me and make this thing, because when you see it running, it is quite a feeling of achievement, which hopefully we're going to get to in a few videos' time, because we're quite late on in the process now. And within the larger scheme of things, I have created shorter playlists to deal with different aspects of this. And this is part of the control unit set, and we've created a whole lot of subcomponents to go into the control unit, and it is time to start finishing, putting it together. So previously we put in the fetch decoding, which is up here, and hopefully, I didn't say so in that video, but you should have saved it so that you could get it back. And what I'm going to do now is I'm actually just going to bring this lot of stuff down so that hopefully we can. Yes, that doesn't work. I was just trying to select those corners at the same time as everything else, which you can't do, unfortunately, DigitalWorks. So I'm going to have to move those corners separately. But what I want to do is to bring this down so that I'm going to put everything else above it rather than below it. That's a small weakness with this simulator. There's a lot of great strengths to it, though. I do love it. So, what we're going to want is some of our decoders, and we're going to do it. Everything is based on on the op, so we're going to have an op input. And in fact, what I'm going to do is I'm going to create a line as if it was a bus across the top that I can tap off the op. 1, 2, 3, 4. And just tweaking the spacing a little bit there to be neat. And I'm going to put, I shouldn't have done 4, should I? Because I can just do copy and paste. You will hear me go at myself all the time as I do this stuff, and that's obviously an indicator that I think I've done something that wasn't perfect. So let's compress this. But we will line them up. Just select the whole thing. If we need to extend it, obviously we can. And as you've seen, I've put a tag on one end, which is we need to connect to an input, and I put an LED on the other end. This is just a habit of mine. We may never see these LEDs being used in anger because we might not be diving down whilst it's running, but it's there just in case, which will help us debug problems if we've got them later on. I'm very into doing defensive things like that. So that's good. Right, so we need a op decoder. In fact, we're going to actually want 2 op decoders, I believe, because we have 2 op phases. And it appears on our op decoder this is probably the execute, but it's not been labeled. Let me just check that. Yes, that's the trigger. Okay. I'm not going to go out and quickly rename that, but I probably really should do. Let's make those a little bit closer. So we've got fetch 1 and fetch 2 coming in with. We're also going to have. Here we go. Tags x1 and x2. We need to do some labeling over here. So this is our op 3 to 0. Let's make that text bigger and rotate it. So 3 is at the top. That's a normal convention for binary numbers, either left to right or top to bottom. And x1. So these are the inputs that come from the ring sequence. X2. There are 4 that we take in, which is the x1, x2, and the fetch 1, fetch 2. Those 2 happen first, and they bring the instruction from the memory and stick it in the here in the op in the op register, which will be connected to here. Okay. So bring this slightly lower so I can take these wires over the top. Which way around do I want these? Does it matter? I'm just going to invert them here, just for the sake of making x1 the one on the left and x2 the one on the right. So I'm going to connect up that to that. And that one to that. Okay. And the operation obviously comes from here. So what the op decoder does, if you remember, is that it looks at the operation and works out which of the 4 kinds of operation we've got, whether we've got a halt, an ALU operation, a jump operation, or a register operation, so a register move operation. And although I'm connecting both of these up, and I've connected x1 and x2, actually most of these I don't use the x2, they just use the x1. You see what I mean, hopefully, as we go along. Right, so we need a decoder for a jump decoder and a reg decoder as well in here. So the reg decoder, right, I have got the wrong ones there. They're the ones that I previously made. I need to go to my macros, which are the ones that we've been making. Sorry about that. Jump decoder, does that look like our jump decoder? Yes, it does. Reg decoder, that's our reg decoder. That's fine. Okay. So what I'm actually going to do is I'm going to bring these a little bit lower. And the outputs from these are going to come down to these lines down here. The inputs mostly come from above. So let's connect up the ops that we need. So this is op 2 is the first one for the reg decoder. And in fact, the jump decoder only needs ops 1 and 0. Okay. And we're going to use, so this is the first phase, X1, this is the second phase. And in the first phase, if we get a halt, we're going to send that out to our halt. So let's connect that up. I guess we're kind of going to subsequently create wires that are going across here and connecting up. And if we get an ALU, then we want to tell the ALU to execute. So that's our execute line down here. If we get a jump, we're going to want to tell our jump to happen. So if that could have been, let's just, oh no, not that, yeah. Just going to pull these down a little bit. If I need to create more space, I might have to do that. So this is the jump execute. And then the reg decoder takes x1 from a reg that's, so that's x2. So it takes x1 from there. And x2 from the second one. So in fact, this second op decoder is only being used for two of the operations, which are the two of the reg operations, which directly use the memory, and so we have to do two stages of stuff. Some of these lines aren't as horizontal as or vertical as they could be, but I'm not too worried. We also need C and Z for our jump. So let's stick them in and wire them up now. And we will label them, even though it seems that this should be completely obvious because they're wired. Be allowed to C and Z. What do we need to do from the outs, from the jump decoder? Well, we need two things. If we have a jump, we need to remember that we've had a jump, because we, when we do the increment to the program counter, it needs to not actually increment when we've had a jump, because we don't want to jump to one place and then move on to the next. So that's one thing. And the other thing that needs to happen for a jump is that we need to, basically a jump is affected by taking the number that's in data. So a jump instruction always has an address to jump to. So that will have been pulled out as part of the fetch cycle and put into the data register. So we need the data to go into the program counter. Okay, so I'm gonna, we need output enable from data, and bus read from the on the program counter, which is that one. I'm going to pull this across to data. Now, if you remember when we were doing the reg decoder, we had some issues if we had more than one thing attached here on any of these lines. And we're going to have the same issue here if we ever have that. What I'm going to do is I'm going to just connect everything up, and then I'm going to look at each of these lines. If there's nothing connected, I'm going to delete it. If there's one thing, then it's fine. And if there's two blobs or more, I'm going to need to do some wrangling and put some OR gates in. So that was the first thing out of the two. The other thing that needed to happen is that we needed to remember that for when we got into the into the increments adding one to the program counter. And there's a fairly straightforward way of remembering this, is that we're just going to use a I want to use an SR flip-flop, set reset, or do I want to use a register? I used a register in the previous version. It doesn't need to be a register. So we'll just use an SR flip-flop. And what we want to do is that, so this is going to remember if we're going to increment or not. So I'm going to have an output from here called inc. And we could have done it the other way. We could have said that we want this to be high if we don't want to increment, but actually it's easier for it to be high if we do want to increment, because of the way that we increment is to use an adder and to push this into the carry in, which is quite nice. So we're going to label that inc. It's another output which isn't part of the other part of the sets of outputs here, so I need to make sure we've got that. We've wired it up, but I don't need to connect it to something else because there's nothing else that's going to connect to it. I know that. And what we're going to do is we're going to make this reset. So go to 0 when we jump. But then at the beginning of every cycle round, we're going to set this back to 1. And so we'll do that as part of fetch 1. So where's fetch 1 here? Tracing which of these lines? Is that one? Is this one here? And we're going to stick that into the set. Going round. And each of those is connected to the enable because I've done it as an SR flip-flop. Okay. It might be better to use a register. I'm trying to think. There's an SR with enable. Actually, what we really want. Tell me what you want, what you really, really want. So let's use the SR latch. Let's actually go simpler. So we call it bistable SR latch. We need to redo that thinking. And we're actually going to rotate that so it's easier to get to the bits that we want. We want Q is our inc, so let's just pull that down and connect that there. And when did we say we were going to set it? When we have a jump. No, we reset it when we have a jump. So let's go to 0 and we set it when we have, I'll just check across fetch 1. Oh, my wires are coinciding. It would be so nice not to have that. I'm just going to quickly rewire this. I should have put that wire in first, shouldn't I? This really is kind of, neatness for neatness' sake, but a certain amount of neatness helps you understand what's going on. Makes it easier to read in that sense. So that should give us the increment for the jump. The jump has come out. We've worked out what we need to do as the result of the jump. Everything else is connected apart from the outputs from the reg decoder. Okay, and we've got these output enable on this side, bus reads on this side, and the two read and write for data on this side. So let's start putting them in. So this is write to data. Right D. This is read data. WD. Oh, sorry, RD. Right, unable to connect two outputs. So that already has an output from something, from there. So I'm going to tap into that and use an OR gate. So let's delete that wire first. And we need an OR gate. We need to remember what we're doing, because I need to disconnect the other one as well. So this is read data. So I'll disconnect this wire. And it was on, I've immediately forgotten what it was connected to. Was it fetch one? Fetch one does both reads, doesn't it? No. Fetch one does PC to, should be doing PC to MAR. But that's not fetch one. It's do we have an undo? We don't. I'm trying to remember what it was linked up to. Right. Read O, read D. It would make sense for them to be connected to the same thing, which is fetch one. From the program counter to the memory address register and read O and read D, I believe. And then fetch 2 does MDR and MDRD, because then they have already been read, yes. And it takes them to open data. So it is fetch 1 that I need. And where was I connecting this? There we go. Right, let's see if we end up with any more of those. So this is bus read B. I could just do it straight down, but I've got several bus read lines to connect, so I'm not going to. I'm going to see if I get any more of these hits with outputs connected together. This is A. We need to be very careful that we actually connect the right things to the right things, otherwise we're going to get errors. So bus read MDRD, and bus read MAR. This may give us a hit. Yes, I thought it would. Right. I always end up in the template editor then. So MAR, not only do I need to check where it is, but I need to remember what it was connected to. MAR was connected to fetch 1. Okay. And we need all gates. And there's no reason not to have it kind of horizontal there. And then the MAR can come from there. And one of them comes from fetch 1, which is this line here. Just double checking that by looking along it. And then the other MAR line is there. Phew, right. So similarly for the output enable, I'm going to start from this end because I'm going to move them around so they kind of stage like that. So again, we're going to see if we're going to need any opcodes. MDRD. I've got a feeling about this, you know. It's MDRD. Yep. All right. So immediately we've got a hit, and we need an opcodes. And what is it connected to? MDRD is connected to fetch2. Okay. And I don't know how much space we're going to need. Let's stick in an opcode and let's stick it on its side like that. And then feed it in. So fetch2 to MDRD needs to go because it's going to go kind of round in a convoluted circle to get to where it's meant to be. In fact, let's move that so it kind of spans there. Let's take that MDRD off there. MDRD, it's just to give us more space. And I said it's from fetch2, so this is fetch2. I'll take it up there and to there, and then out from here and down to the other end, put this opcode. Little crazy using the opcode as a bridge over those other wires. It's not necessary, but it helps with our space a bit. Does it make that hard to read? Don't know. Data. We have already got one connected to data, so we are gonna need to, whether that flags it now or not, we're gonna need to do an OR gate there. So let's again chuck that around, and we're gonna make it about there. And so we need to know where that's come out of. It's come out of the jump decoder. So let's delete that line there. We're going to take it along at the same level as it was. Take it up to there and out of data here. I need that to be further over. Let's just put another corner in. And then come straight down from there to data. A, nothing else connected to A. Which is reasonable because A is really only subject to stuff with data being moved around and then goes into the ALU. Similarly with B, and then ALUX, again, nothing connected to that. Right, so I think that's all of them. I'm having a look around at everything here. So firstly, I'm going to do a check that all my macros have got everything connected that I think should be connected. So I've got an opt decoder here. We've got stuff connected to all of the inputs and outputs. I've got opt decoder for X2, and that's only connected to reg, and that is correct because we're only going to use that second cycle when we're doing register transfers that involve the memory. Reg decoder, that's all connected, that's all connected, that's all connected, that's all connected. So that seems reasonable. Jump decoder, that's all got connections. Whether everything's connected that needs to be, I'm not entirely sure. We've got an SR latch, so we've got S in our set. We've not got anything out of not Q, but that's fairly normal. That connects to the ink. We've also got four opcodes which are connected to all sorts of things. We've got X2 and X1 which are connected to the opt decoders, which is what they should be. Fetch1 and Fetch2 have been dealt with directly by using those gates and wiring them up. The jump decoder, we've wired that up as we need to, hopefully. So let's have a look at these sets down here, and where there are things we can get where there are pink should mean there is nothing connected and we can get rid of a line. And we need to check that there's no double dots on any line, although they did seem to be coming up. It would only not work if one of them was connected directly, I think, to a tag. I'm not entirely sure about that, but we will check for the blobs along. So MAR output enable, nothing's connected to it. And we're going to ask ourselves the question, is that reasonable whenever we have one of these? And is it reasonable that you're not going to want to read from the memory address register? Yes, it is. We only want to tell the memory address register what an address is. MDR0, one blob. MDRD, one blob. OP, so that's our operation. Do we ever want to read our operation? Well, it's hardwired up here. So no, we don't want to be reading that anywhere. We want to write that in at various points as well, so it's part of the fetch cycle. Data, one blob, and that's one that had an OR gate on it. PC, one blob, and that's on the fetch. So yes, that's right. We're going to need to use the program counter to work out which is the next operation. A, one blob, B, one blob, ALUX, one blob. Right, so for bus read, are we ever going to want to write to these things? So memory address register, yes, we are. We've got a blob, but it's just one blob. Memory data register for operations. So this means when the computer itself, the CPU itself, cannot rewrite its program, and that's that's reasonable. So that's fine. MDRD, we might want to write to the data half of the memory, so that's okay. Op, yes, we do want to be bringing the op in from the memory. We've just got one blob. Data, one blob, and a little surprised that that is only connected once, but actually that's reasonable because that's just going to happen when we do the fetch, and then we use that data in several different ways. Program counter, so that may feel unusual that we're going to read the program counter, but that only happens when we're doing a jump, so that's fine. We've got A and B, and that's fine. ALUX, yes, we're never going to want to write to ALUX because that's the job of the ALU, so that's fine, that's disconnected. Across here we've got a halt, so that's fine, that's good. We've got read from for operations. We've got we don't have write for operations, and that again is reasonable. We don't want to be able to rewrite the program. The CPU shouldn't have the ability to do anything with that, so that's fine. Read data, yes. Write data, yes, we might want to do that. And execute, we definitely want to do that. So that hopefully is our control unit all wired up. Now we've got a fairly big template to create for this because we've got a whole load of stuff out here. Output enables bus reads and several other things. So let's have a look at the template. And we've got nothing there at the moment. We're going to keep that box. I'm going to get rid of that. I'm going to make a big box. And I need to make some quick decisions about how I'm going to deal with where I'm going to put things on here. And should I make it? Well, I wish I could make it tall and thin, actually, because I'd like to be able to take everything out of the side, but I can't. So let's work on the principle that if I want to take stuff out the side, I'm probably going to put them on the bottom and then rotate it for when I use it, which means it's probably going to be more useful if I put annotations on the side. Let's kind of work on the idea that it is going to be is going to be put upright. Okay, so I'm going to put all the outputs along here. And we've got some output enables, we've got some bus reads, and we've got some general purpose ones, and we've got ink as well. And then I'm going to put all the inputs across this side here, which is going to become the right-hand side. And I'm just thinking about my diagram and how this was set up. Actually, what I'm going to do is I'm going to put op in at the side, so that then becomes the top. And that works fairly well with the, I'm just kind of thinking through in my head how I might put stuff together in the CPU. And then having the rest of the stuff on that side is fine. There's quite a lot of this to do, so what I'm going to do is I am going to put the fast forward music on whilst I do this. I'm going to see whether I decide I need to pause to say anything before I actually then do the wiring up as well. But hopefully all in one phase, I'm going to put all the bits on here that I want, and then also put the do the connections that I need. So here we go. So that should be everything wired up. Let's save it. It's already called control unit. We've saved it a couple of times before, so just save should do. And let's have a new circuit because we are going to want to test this control unit. Where's my control unit gone there? Okay. My text on the left-hand side is all a bit wonky. I wondered if it would be a problem if it was at an angle, but there are various different angles. However, it is what it is, and I can't be bothered to straighten them all up, so we're going to leave them as they are. I hope yours is neater. That would be good. Right, so I'm going to chuck in some inputs. Oh my goodness, my inputs and outputs are all wonky as well. Did I rotate this correctly? I think so. Everything looks wonky. My great wonky control unit. So lots of outputs, quite a few inputs. So once again, let's speed up the process. Right, there we go. And in order to test this, we're going to want our opcodes to check against. I'm going to check all the opcodes as well as the fetch execute cycle. So let's start simulating. Okay, this thing has set itself up already, which is great. So fetch 1, can we remember what it needs to do? It needs to get the program counter and put it in the memory address, and then grab the operation out of the data. So it should do, the top half is from, the middle bit is to, the not half, the thirds, and then extra stuff is the bottom. So fetch 1, program counter, 2, memory address register, read out, read D, that's fine, and inc is set as always. Fetch 2 should then bring that the other way, so it should be MOR and M, so MDRO and MDRD into op and data. MDRO, MDRD, op and data, and they go by separate buses, so there's no confusion between those. Right now, at that stage, when everything's connected together, the op will hold the operation. And we need X1 and X2, and so we're going to check these. So X1 is halt. Yes. Sorry, X1 for 000 is halt. Going to check X2 for everything? I think maybe we need to. So 0001 is an ALU operation, and all we need for ALU operations is for it to ping the ALU, because that operation data is also going to the ALU. So let's do X1. What's this doing? 0001. X1 is giving us data to the MAR. And why is it doing that? You would think that it would do that if we were doing a data read. And so that should only be happening for data transfers. Okay, but what we've done, so here's the first error that we've made, is that in the reg decoder, we have not paid attention to whether it's to what kind of thing it is, but it shouldn't be sending anything to the reg decoder unless it's actually a reg thing. So I was just checking if we might be wired up backwards here. Because 1000 is this one here. And I think this is potentially being likely. Let's see what happens if we imagine that we're wired up backwards, and we get a halt for 0001. Something is not right here. That gives us a halt. What does that give us? Nothing. How very strange. Let's dive in here and see what we've got going on. Let's set that one again, and next to one, and dive in. This is why we test. So op 3 x1. It should be, our op decoder should be saying that, oh. So I'm curious about the fact that, that doesn't seem to be connected. So possibly the problem here is that I've connected one of the templates tags, which is that one. No significant bit. The other thing is that so that's 3 to 0, and have I done it the other way around? I'm going to have to go back to the control units. So let's go up and save this. I don't know why we're there. Testers, and we're going to call this the control unit tester. And then we're going to reopen the control unit and stop simulating. And the template editor. So actually, we don't have all 4 of those connected, and this may be reversed because it should be 3 at this end, and I've got them at the wrong end, I think. So pin 3, and that tells us that that's pin 3 there. Oh, the order seems strange, right? So what do I want? I want that to be pin 1, and that's pin 4. So all I'm going to do is I'm going to wiggle these around here. That's pin 1, and that's pin 3. That should be pin 2. Does this tally up? I've got 1, 3, 2 above, just not helpful. So 1, and then actually I need 3 next. What on earth was I thinking? And then that should be 2. And this needs to be connected to 4. So I need to close that, highlight this. Okay, save. Glad I caught this here. 1, 3, 2, 4. Let's double check that template. 4, 2, 3, 1. No, 1 is op 3. So it's 1, 2, 3, 4. Sorry, 1, 3, 2, 4. There should be 1, 3, 2, 4. That's correct. I'm looking down here at the thing to tell me which pin's selected. So I did save. I'm going to reopen the tester. We don't seem to have the tester in there to reopen, so let's do file open. Circuit has changed. Yes, save the circuit. Control unit. Right. Then it doesn't go on to open my macros. Now I want the tester's control unit tester. And unfortunately, I have to replace that. So a certain amount of wiring to do. Amazingly wonky control unit. Am I going to talk or am I going to play music? Which would you prefer? Whichever it would be, it's obviously going to be the one that I'm not going to do. I seem to be partway through already, so I'm not going to play the music. I'm just going to keep going. Once again, we have seen the value of testing, which is a very classic lecture thing to say when something goes wrong. And to be honest, I don't feel at all like I have failed in that something went wrong. I don't feel that in this process that I need to do everything perfectly the first time. I don't think it is bad for you to see me make mistakes. I don't feel like my ego needs you to not see me make mistakes. But I do feel like I like to keep editing down to a minimum. So if we keep going, that would be good. Right, let's go back to our testing. Right, so we're on x1 with 0, 0, 0, 0. That should give us halt, and it does. That's good. All right, 0, 0, 0, 1 should give us ALU. It does. And we don't care what ALU thing it is. Let's do the next one. 0, 0, 0, 0, 1, 0 gives us ALU, execute, that's fine. The next one should be jump, which is data to PC. That's fine, that's exactly what we expected. Let's go to 1, 0, 0, 0. 1, 0, 0, 0 is an ALU. And interestingly, ink has changed there. And that's because we did a jump, but it hasn't. That's because we haven't done fetch 1, which will reset. So normally it'd do a cycle, and we would do fetch 1, which would set that back. Okay. So I've got to feel every time we do a jump, I think we need to do that to make sure we're checking that. 0, 1, 0, 1 is a jump, so it's jump conditional on C. So at the moment it's not jumping, let's hit C, and it does do the jump. Okay, and as soon as we do the jump, it turns off the ink. Okay, so let's do fetch, and we've still got execute on the ink, and we're going to hit C again and watch the ink go off. There we go. Right. Hit that fetch again. It doesn't matter that we're doing both of those. That will just set that nicely. Right, next 1, 0, 1, 1, 0. That's jump now Z. Okay. So yes, that's happened because there's no Z, and if we put Z on, nothing happens. So that's fine. Let's take that off and reset our ink. There we go. And X1 back on. That's going to reset it again. Let's go to the next number. 0, 1, 1, 1. So this should be ALU. Yes. We're up onto the second column now. 1, 0, 0, 0. So the data transfer ones for X1 should just be taking the value in data and putting it in the memory address register. Let's see if it manages to do that. I've got to switch that off while I change the number. So it goes data to MAR, that's correct. Well, the next one should be an ALU. There we go. Next one is an ALU. That's correct. The next one should be a data transfer, but it shouldn't do anything because X1 only works for the ones that are involved with the memory. So nothing happens. That's correct. Let's go to here. And then this one should be another one that's connecting to the memory. So it's data to MAR. So this is 1100. We will check the execute 2 for all of them as well. And then the next 3 should all give us nothing as a result. And that is correct. So that's half of it checked. We're going to now check X2. So the only things that should happen here should be when we've got register transfers. So if we leave this most significant bit as 0, I'm going to test all the others. So let's run through all of the numbers. This, nothing should happen. Nothing, 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 nothing. I think I've checked them all between those changes. So let's put the one on. So this is, we've already got the information. We've already put the data in the memory address, and this is going to go from A to the memory data register and do a write of data register. So that seems good. 1001 should give us nothing. That's correct. 1010 should give us nothing. That's correct. 1011. So from A to B, that's correct. And then the final four. This is memory data register D to A, and it's a read of the data at the same time. So that seems reasonable. This should be data to A, which is correct. There should be, ALUX to A, that's correct. And then finally, we've got B to A. So we've been through all of the opcodes. We've been through X1 and X2. We've checked the fetch and the execute. Everything seems to be behaving as we would expect it to. So we've created a control unit. It's a little bit wonky, or it is, mine is. And if I can be bothered, I will fix that. But otherwise, that's the end of this little series, and we're coming to the final series in this creation of the CPU, which is when we start putting everything together and creating the CPU as a whole. So it's all very exciting. Come back and join me for that series of videos, but that's it from me for now.